Good evening, everyone. I am Mr. Ish. Thank you for joining me. We're looking here at a single, interesting, but slightly difficult question. Having the Bernoulli's form, we have to solve this differential equation. Why is it of that specific form? Because it looks like this. You have something which is dy over dx plus py is equal to q times y to the power of n. That y to the power of n makes it non-linear, and hence it's a Bernoulli's form. This item right here is exactly what you see right here, the y cube. A logical first step can always be your substitution. Z is always equal to y to the power of 1 minus n. What's that n value? It's exactly that 3 right there on top of this y. Z is equal to y to the power of minus 2, and then the derivative of all of these, dz or dx, is equal to the derivative of that. Use the power rule, minus 2y to the minus 3 dy over dx. And that's exactly what you will bring into play momentarily. The next step should be to get rid of that y cube on the right hand side. Hit everything by 1 over y cube and see what happens. You'll have y to the minus 3 y prime, which is same thing as dy over dx. So let me write it as a dy dx plus y to the minus 2 tan x is equal to secant to the 4x. And that right there is everything coming into play. Remember, our equation is dy over dx plus y tan x is equal to y cubed secant to the 4x. What's the next step? Well, I'm seeing a minus 2 over here. If I multiply everything here with a minus 2, it will allow me to bring all of those substitutions into play. And I'll have minus 2 y to the power of minus 3 dy over dx. Minus 2 y to the power of minus 2 tan x is equal to minus 2 secant to the 4x. And now everything falls into play. Minus 2 y to the power of minus 3 dy over dx. I'm seeing that here. That substitutes for dz over dx. I have a y to the power of minus 2, which is z. I have a minus 2z tan x is equal to minus 2 secant to the 4x. Now it looks like a linear form. You know I have to determine the integration factor, and I can do that. I have this p value right here. It's always e integral as an exponent p dx, but p over here is what? It's minus 2 and tan x. Minus 2 tan x dx. Now this right here is going to lead to your integration factor. You're really looking here at e integral of minus 2 sitting outside, and then tan x dx. You know tan x dx is what? You're getting here e to the exponent minus 2 natural log secant x. But this minus 2 can also be brought right here as a minus 2. When you're looking at all of that, I'm going to rewrite this by properties of logs. You're really looking at e natural log, e exponent natural log 1 over secant square x, which if you are cognizant of the fact, you can bring its reciprocal. E exponent natural log cosine square x, which all boils down to cosine square x. You know, you can use properties of logs. Y is equal to e exponent natural log cosine square x. You can do a natural log y is equal to a natural log cosine square x ln e. This goes away. When you bring everything onto that side, I can work it out for you and just show you. You'll have natural log y minus natural log cosine square x is equal to 0. Bring everything under a common log. Y over cosine square x is equal to 0. Take the natural log on the other side. You'll have y over cosine square x is equal to e to the power of 0, which is 1. And when you take this cosine square x, you get exactly everything here as your integration factor to equal cosine square x. Hence, that is our integration factor. And I worked it out for you, and you've seen it. That integration factor now will come all over here to your linear form, and you'll multiply it across with this cosine square x. When you multiply it, you get cosine square x dz over dx minus 2z. I'm going to multiply tan x with the cosine square x. If you simplify tan x and cosine square x, you really get a sine x and cosine x. Because this is really a sine over cosine, it cancels out one of that cosine from that square. Anyhow, from here, cosine square x and secant to the 4x, it will cancel out two of these units. You'll get secant square x. And that right there is our linear form. And this is not hard. When you look at this left hand side, it all comes from the implicit differentiation of an item. And that item is d over dx. Well, you're going to look at this z and you look at this cosine square x. And that's exactly what it is. Z cosine square x. If you do the product rule, implicit differentiation of this, you will, I guarantee it, get this. And it'll be right. Anyhow, You have a minus 2 secant square x. Bring the integrals in here. This cancels out. You really have z cosine square x is equal to minus 2 sitting outside. But what's the antiderivative of secant square x in terms of its integral? You know what it is. It's tan x plus c. Now, we're very close. I want to do a little bit of shuffling over here. I'm going to take the z on the other side. Cosine square x is equal to minus 2 tan x plus c over z. But what was z? Z all along was equal to y to the power of minus 2, and I can bring that into play. Y to the power of minus 2. But isn't y to the power of minus 2 really it coming up as a positive exponent? It sure is. Cosine square x is equal to y square minus 2 tan x plus c, and that right there would be your answer. Cosine square x is equal to y square parentheses minus 2 tan x plus c, and that right there would represent the function or the equation for which this differential equation is true. dy over dx plus y tan x is equal to y cubed secant 4x. If you want to write this in a better way, you can, and I'm going to write it for you right here. Cosine square x is equal to y square and then parentheses c minus 2 tan x. This way I have the positive component first and the negative second, and this here is a good answer. That right there is also a good answer, and this equation, the Bernoulli's equation, has been solved for you. And you know everything started right here with the elimination of this, because we had something which was equal to q y to the n. This y to the n had to be eliminated, hence we divided everything here by y cubed. We did our z substitutions, and you know we did the dz or dx. We brought the power rule for that, and then everything follows from there. And you've seen this, you have seen previous examples in the other 2 videos on Bernoulli's equation. We'll probably be looking at some more examples, because this right here is a difficult differential equation to get a handle of, but again everything is still here first order. And that's it for this video. Thank you for joining me. Have a good day.